control. And for our first session, we are pleased to have Dr. Bharani Chandra. He is currently the professor and head of EEE at GMR Institute of Technology, Andhra Pradesh. He was awarded his PhD degree by the University of Leicester. He also was a postdoctoral researcher at the University of Exeter. He has publications in referred conferences and journals, and he is also a reviewer to various international journals. I welcome Dr. Bharani Chandra for our first session. And I always also request all the participants to kindly mute their mics and off their cameras for a better clarity. Thank you.
Hi, good morning, everyone. Shall I go ahead?
Yes, Bharani, we can start.
Yeah. Thank you for the introduction. First of all, I would like to thank Dr. Elizabeth Rita Samuel, who has invited me to deliver the lecture on 5 days online FDP on control system applications with MATLAB session at Rajagiri School of Engineering and Technology. I would also like to thank the management of Rajagiri School of Engineering and Technology for giving me an opportunity to present in this FTP. Today we will be discussing about control and state estimation, past, current, and future trends. And the hands-on session, as far as the hands-on session is concerned, we will be discussing the PID controller or PID tuning in 1 minute using MATLAB. And myself is P. Bharani Chandra Kumar, and I am an academic at GMRIT of Technology, Rajam, Andhra Pradesh. So this is the outline of the talk. So I will start with a brief introduction to the past and present controls. And these are some of the control designs what I will be discussing very, very briefly. I will not go into much detail. And the estimators as well, the key estimators which are being used in the industry and by the academics from the past few decades. And then the future of the control systems. What is the future of the controls? And finally, I will conclude with the hands-on session on PID control design using MATLAB in 1 minute. So this aspect will be very much interesting, the number 5, because as far as our experience is concerned, many of the researchers struggle to find the PID controllers or exactly finding what is the KPKI and KD gain for a particular system. And some people, due to the lack of the knowledge in the design aspects or the utilization of the advanced tool, they keep on tuning the controller for the edges, and finally they get the success in a very late time, but it is possible to get the desired response by tuning an appropriate controller in 1 minute. So that will be the last part of this particular talk. So the controls, so the fundamental questions one has to ask: why the controls? The answer is controls requirement is everywhere. So in general, the control systems in the control literature is called as the controls. So the controls requirement is everywhere. Everywhere means everywhere. It could be the domestic, it could be the industry, or it could be defense, civil applications. Wherever you see, there will be a requirement of control systems. The two key parameters which is required, which is to satisfy the control system design with the stability and the performance and robustness. These two aspects have been very well understood in the control community since last maybe 1 century or so. So people has been working in this area, the stability and performance and robustness. One can assess the stability, a nominal stability from various aspects. One can find out the stability if you go to the standard control system textbooks. From the pole locations, one can find out the stability. From the definitions of bounded input, bounded output, one can find out the stability. And one can view the stability from the time domain response, and one can find the stability from the frequency, margins as well. So that was the once upon a time it was the very much required thing. However, now the control is very much matured, and the performance and robustness. So the design controller should satisfy the performance as well as it should be robust to the uncertainties in the plant parameters or the uncertainties which might be arising from the external disturbances or exogenous signals and so on. So these 2 points, the stability and performance and robustness is not of much concern now because control is very much matured and satisfied. The main concern now, the control engineers which focusing are on the security and privacy aspects and humanity. From where the security and privacy is coming into the picture. So nowadays, you might be aware that once during maybe a decade before or so, people were very much interested in connecting the sensors to the wires and so on. However, now due to the advancement in sensor technology or the network technology, uh, the real connection between the sensors, hardware, or the actuators or the plant is no more the wired one. So most of now people are going through the era of cyber, the so-called cyber physical systems or IoT control and so. So where most of the sensors are connected through over some network, either it could be the Wi-Fi or through it could be the private network or so. So the problem here is when we are trying to get the data from various sensors through the networks or through Wi-Fi or through any other such medium, wireless medium. So the main concern there is security and privacy. Are you ensuring that whatever the data has been sent from one terminal to another terminal for the control purpose or for analysis purpose is secured or not? Is my data is being tampered by someone, or the data whatever has been sent from one has been sent from one the data which is being sent from one particular node, whether it is exactly is reaching to the another node, required node or not. If the data is not reaching from one node to the another node, whether it is due to the data loss, which could be due to the bandwidth issues, or somebody is tampering with it. So these are all answers need to be addressed by the control engineers along with the data scientists and other things. So now the control systems is not about only designing the controller. So designing the controller is a small part of the whole control system applications, which includes now the control system includes not only the stability and performance and robustness, it should take care of the security and the privacy aspects as well, and the humanity as well. When the man in the loop, or can the control systems engineer can provide some solutions to the humanity? This is a big question which we'll address, at the future of controls and so on. So these are the two key points, which is the need of the hour as compared to the first two. The first two is okay, it is necessary and essential, and it is being, anyone can design the stable controller which will ensure the performance and the robustness. So that is fine. But these two are the need of the hour. The second part, what is my controls and state estimation? So the state estimation, why? So as far as the control system design is concerned, we need the information, some kind of feedback. If it is a feedback control, we need some information through the sensors. If we use the complete full state uh, feedback controllers like LPR or some other controllers, dynamic inversion controllers, we need the full state information from the sensors. or for some fault tolerant control purposes as well, fault tolerant controller design as well, we need the full state information from sensor. And in realistic scenario, we never want to use the full state information. For example, for a typical plant, if there are 300 states, so we don't want to use the 300 sensors to for the control purpose or for the monitoring purpose or the fault tolerant control purpose. What we do is the concept of state estimation can be used when the full state information from sensors is not available. Either either due to the sensors, all the sensors are very expensive or unreliable, or the sensors which are very noisy and bulky. So we cannot completely rely on the unreliable sensors, or we don't want to use the bulky sensors or the noisy sensors. So is there a way where instead of the complete state information, can I reconstruct or can I estimate the states based upon reliable sensor? For example, if a particular plant has 100 states, if a particular plant has 100 states, and I assume that 50 sensors are reliable, which are very good, cheap, and I can completely trust on the 50 sensors, and the remaining 50 sensors are not at all reliable, or they're very bulky, or they are very noisy, they are very expensive. So the concept of state estimation can be used to estimate the 50 unwanted sensor information or the unwanted sensors by using the first 50 or the 50 good sensors or the good sensors from which I can have the reliable information. So in a way, by using the state estimation, I can reduce the total number of sensors from 100 to 50, provided provided I cannot simply use the state estimation, provided the plant should be observable or it could be detectable in some cases. So this is the philosophy of behind the combined control and state estimation. So you can see this is the plant and this is the output, and the input which is going to the plant is given to the state estimator, and the state estimator estimates the complete states. For example, if the plant has 100 states, I assume that only 50 states are available for measurement, which I call it as output. So what is going here is to the Y is only the 50 state information, and the control information, what is going to the plant, the same is been given to the state estimator. And based upon these two inputs, which to the state estimator, I can estimate the complete 100 states. And these complete 100 states can be given to the control systems. So in another case, what I can say that people might argue that if I use a very simple control strategy, which may not need the complete state estimated state, then what to do with it? Then why the state estimation is required? For example, if you consider a simple example of a DC motor where there are two states, one is the current and the second one is the speed. I want to control the speed of a DC motor. So theoretically, I need only one sensor measurements. That is the speed, output speed from the DC motor. So in this purpose, why one has to go for the state estimation algorithm, or what is the requirement of the state estimation algorithm? So what I can say that if I want to go for a sensorless control, or in a way I say that sensorless means here mechanical sensorless control. That means I don't want to use the mechanical sensors for the state estimation. Rather, is it possible if I use the current measurement, and from the current measurement, can I calculate or can I estimate the speed, and the estimated speed is being given to the error detector or the error comparator, and whatever the error has been generated, from that the control can be built up. So in this particular case, you see that though there is only one output, the speed is required for the PID controller, but I don't want to use the mechanical sensor or the speed sensor due to whatever be the reason. In that case also the state estimation is required. So my whole control, though I want to control the speed of a DC motor, but my sensed output is current. So the electrical sensors I am going to use to control the mechanical speed. So that is one such application where this state estimation is required. This is very classical example what I'm going to explain the concept of brushless DC motor. Consider a brushless DC motors with 5 states, 3 control inputs and 3 outputs. The 5 states are 3-phase currents, IA, IB, IC, speed and rotor position. And the 3 control inputs which are going to the plant are VAB, VBC, VCA, and the 3 outputs are IA, IB, IC. So you can see that I'm using only the 3 outputs, whereas I need the complete 5-state information for my control purpose or for fault monitoring purpose or for some applications. So the control or the monitoring mechanism, I assume that it needs the complete state information. That means all the 5-state information of all the 5 states are required. However, for the practical cases, I have only 3 sensors, IA, IB, IC. 3 sensors are there. These are the current sensors. I don't have the position, the speed and the position sensors. So now the concept of estimation can be used, which says that from the outputs and inputs, based upon the outputs and inputs, I can estimate all the states. So the outputs, these 3 outputs, and these 3 control inputs. From this, I will estimate the remaining 2 states as well. So that's what is the control. That's what the concept of estimation can be applied here. And then what I'm going to use is combined control and estimation. In the combined control and estimation, instead of the actual states, I will fed back the estimated state. And I assume that my estimator is very good. That means the estimation error goes to 0. My estimation has been designed in such a way that my actual states and the estimated states are very close. So these are the some of the control resources if somebody is want to pursue research in the area of control systems, then I suggest that one should go with the standard journals, and these are the some of the standard journals which the control researcher from throughout the world who publishes the good works, and getting in this getting accepted papers in these journals is not that easy. So the IEEE transaction on automatic control, which is in general called as a TAC or ITAC, Automatica, IEEE transactions on control systems technology or control systems letter is also nowadays in the last couple of years that is a new journal, IEEE control system letters. IJC, International Journal of Control, European Journal of Control, IET Control Theory and Applications, International Journal of Robust and Nonlinear Control, Control Engineering Practice, Asian Journal of Control, IEEE Control System Magazine, and many more. So this list is just indicative list. It is not the complete list. So there are many more journals as well. If you want to see the recent update in the control systems, then one can refer these journals. And some of the standard conferences in which one, if you get a chance to attend these conferences, please don't miss it, because this is the conference where the researchers from throughout the world, the top class researchers, present their work, which is IEEE CDC Control and Decision Control Conference, ACC American Control Conference, IFAC International Federation of Automatic Control World Congress, and there are many more. And some of the control experts who have been contributed in the recent past, maybe in the last 2 or 3 decades, who has contributed to the control systems from various different types of control systems includes Richard Murray, Stephen Boyd, Alberto Isidori, Bruce Francis, Pramod Khargonikar, M. Vidyasagar, Leonard Young, Murari, Doyle, David Q. Main, Hassan Khalil, Massajoski, Anuradha Annaswamy, Mohammed Darouch, Ian Postlewaite, Davaigu, Christopher Edwards, and many more. So these are the control experts. Again, these are some of the control experts which whom I closely follow, and and these and whatever you are saying, that they have contributed very much to the control theory in the last uh, couple of decades or so, 2 to 3 decades. Before designing any control systems for any realistic applications, real applications, this is the typical flow which most of the industries typically, or the labs research labs, they typically follow this typical flow for the systems and control. The first thing is system modeling. So unless if you are going for the model-based system, then you need to have a model-based control system. Then you need to have some kind of model of the system. So how to get this model? Either one can get, if it is an electrical systems, then the fundamental thing is apply the KVL or KCL. If it is a mechanical systems, use the Newton's laws. Sometimes we can use the concept from the physics, chemistry, biology, or so on to come up with the system models. Basically, the system models are nothing but expressing the systems in terms of the differential equations, mainly in the terms of the differential equations or ODs or PDs or so on. In case, in case if the system is very complex, or if you don't know what is, if you don't know what is inside the system, then what to do? Then during those cases, one can use the concept of system identification. System identification is nothing but assuming the system it as a black box, excite the system for different kinds of inputs and observe the different kinds, whatever the outputs you're getting from that excitation. And from the relationship between the input and output, try to come up with some model. That is called as a system identification. A very simple example, if a black box is given to you, and if the input to the black box is cold water, and if the output is hot water, you don't know what is this black box. But since you know that as soon as if I get the input is the cold water, and after some time if I'm getting its output as a hot water, then you can predict that system has some heating mechanism in it. Either it could be some geyser or some coil or some kind of heating mechanism. The same philosophy or the same concept can be applicable to the system identification as well to find the black box systems or the systems which is very complex or the systems which are unknown. We can use the concept of system identification. And the next step is selection of suitable sensors and actuators. So these particular steps will tell us we have to carefully select the sensors which are reliable and the actuators which could able to meet the bandwidth of the inputs and so on. And the next thing is control system development. So in the control system development, I say that is a combined, including the state estimator. So when I say the control system design, by default, it has the state estimation mechanism in that one. So I will start with a very simple linear model, and then slowly I will try to understand the system's behavior, and I will try to correlate with the realistic behavior of the system. And slowly, I will keep on increasing the system complexity by including more and more physical constraint in that one. And that's I say it is a high fidelity simulations. That means as much as possible we try to include, we have to include all kind of possible non-linearities and possible kind of parametric uncertainties which the plant will see, and your control system should be able to reject the disturbances and so on. So high fidelity simulations means as much as try to use the system model as much as close to the realistic uh, system, and then try to do the hardware in loop system. The hardware in loop system is something in between the simulation and the hardware. So in the hardware in loop systems, we will not completely replace the complete simulation model with the hardware. Rather, what we do is some of the elements we will keep as it is, and some of the elements we will use the hardware. For example, in the classical control systems simulations, what we see the plant, actuator, the sensors, and so on. So in the hills, what in general they do is they try to replace the sensors in the simulations with the actual sensors and the actuators with the actual actuators. And whereas the plant will be the model, the symbolic model or some dynamical equations and so on. So here it is a combination of simulation model, which is the plant, and the combination of the other parts are the real one, the sensors and actuators. So in that way, it is one can ensure the certain kind of realistic uh, scenarios or realistic applications, which is very close to the real life and so on by using the hills. Once after getting the satisfactory results in the hills, then they go for the lab scale or prototype development and testing. So instead of directly deploying this, whatever the hills to the realistic system, they go for the lab scale or prototype development and testing. And then they will apply the full blown system model and testing. In this, they will try to, and they will check various, they will inject various uncertainties, including the parametric variations, and they will check the safety levels, reliability, fault tolerance, and so on. And once this has been satisfied, then they will go for the mass production, provided this should be certified by the certified engineers, and they do all kinds of, if it passes through all kinds of tests and so on. And then finally, final step is mass production. So this is a very typical flow. More or less, most of the industries follows these steps. Some industries may skip one or the other two steps, but this is the typical flow for systems and control design. And now the past and present controls. So this is the brief timeline for the past and present controls. So the Lyapunov stability theory, which was developed in 1890s by the Russian mathematician Lyapunov to find the stability of nonlinear equations and so on. Though it was in 1890s and so on, but still now the people, when it comes to the nonlinear stability theory, 99% cases the researchers rely on this Lyapunov stability theory to find the stability of the equilibrium points of the nonlinear systems and so on. In 1910s, early 1910s, the PID controllers were proposed for various applications. And in 1920s to 30s, the emphasis was on the frequency domain analysis by using the Nyquist and Bode plots. And then slowly the paradigm has been shifted to the programming and optimal control, which is basically a time domain analysis or the time domain approach. And in 1960, which was very crucial era as far as the control theory is concerned, and by then till 1960s, since the system design or the controller, as far as the controller design is concerned, it was very much well understood by the control engineers throughout the world. And if somebody applies for the project in the control system area, the agencies, the funding agencies, simply they reject in late 1950s or so. And they say that control systems is very well understood. We are not interested in exploring further. However, in the 1960s, the era which is called as a modern control theory, which gives a complete new picture to the system analysis. And it makes the system analysis very simple. For example, so the so-called state space equations or so-called the controllability and observability and the Kalman filters, they were all developed in the 1960s or so on. So the advantages, how can the researchers could convince the funding agencies that control system is required, basically when it comes to the multi-input, multi-output systems. When it's single input, single output systems, yes, you can design the PID controller very easy. However, when the complexity increases, when more number of inputs come into the picture, more number of output comes into the picture, then instead of the once a single transfer function, it becomes a matrices of transfer functions. And then you have to design the independent controller for each of these transfer functions, and you have to look for the coupling effects and so on. So that makes the systems very complex. However, the modern control theory, whatever be the, it doesn't matter how big your the number of inputs and outputs, you can simply represent the A matrix is n by n, and the B matrix will capture the complete input information, and the C matrix will capture the complete output information. And the analysis is very easy for the multi-input, multi-output systems and the systems with non-zero initial conditions and so on. And in 1970s, again, there was a shift from the classical modern control theory to the adaptive control theory. The adaptive control, yes, now I have the controller. Yes, I can design for the multi-input, multi-output systems. Then what will happen if some of the parameters of my plant changes with respect to the time, with respect to the environmental condition and so on. So the controller, the controller which I have designed for the nominal plant may not work if your plant parameters are changing with respect to the time. For example, if I want to design the controller for simple RLC circuit, I assume that R, L, and C are constants. Suppose I have designed the PI controller, PID controller, then everything looks fine. But due to some practical reasons, if this R value changes, L value changes, or C value changes by 20% or 25% from the nominal values, then the controller which I have designed for the nominal values, then it will not give the desired response. So the concept of adaptive control has come into the picture mainly to cater the aerospace industries to start with. They where the plant parameters changes very frequently. So this adaptive control concept is has been from the 1970 onwards. They played a crucial role. So in this adaptive control, the control structure or the control parameter adapts as per the change in the plant parameters, and it gives the desired performance even in the presence of plant parametric uncertainties or so on. So here the plant parameter changes with respect to the time as plant parameters as well as control parameter also changes. However, in the 1980s, people have thought that the researchers have thought that adaptive control is quite good. But the problem here is I should have the high computational processor required because it needs to, keep on changing the controller parameters with respect to the change in plant parameter. In the robust control, the it is different, though it can also able to deal with the plant uncertainties and so on. However, here the control structure, the control parameters are the constant, whereas here the control parameters varies with respect to the change in plant parameter. So this robust control technique can handle, can able to deal with certain computational issues with adaptive control. But the problem with the robust control technique here is the order of the controller could be very large. It could be, as minimum as the order of the plant, or if they're including more weights, then the order of the plant will be very high. Though then the concept of model reduction one can use to reduce the total number of states of the controller and so on. And 1990s, the extension of the robust control theory for the state estimation has been used, and which is called as the H-infinity filters. And 2000 and so on, the sigma point filters, the whole bunch of sigma point filters like uncentered Kalman filters, particle filters, and so on, was proposed in 2000 or so on. Here, the concept is the problem with the Kalman filter or the H-infinity filter is basically they have been designed for the linear system. However, when we want to apply for the nonlinear systems, we have to go for the Jacobian approach, or we have to expand the nonlinear systems by using the Taylor series, and only we restrict ourselves to the Jacobians or the first order approximation, and the higher order approximation we assume that they are zero. However, if the higher order approximations we are approximating it to zero, if they have some critical information about the plant which we are trying to eliminate, then the estimate may not work. So the concept of sigma point filters is to avoid some of the uh, is to avoid some of the limitations or what one can face in the normal Kalman filter and H-infinity filter when it applied to the nonlinear systems. And they are called as the extended Kalman filter and extended H-infinity filter. So in 2010s and so on, so the concept like the sigma or uncentered Kalman filter, mainly there are some ad hoc parameters in that particular uncentered Kalman filter, which are alpha, kappa, and so on, which one has to tune based upon some heuristic analysis. In 2010 and so on, the cubature Kalman filters were proposed by Simon Hyken and their group, where they were more focused on developing the more theoretically uh, proven Kalman filters for the nonlinear system. And numerically, this sigma point or the uncentered Kalman filters were not, more specifically in the sigma point filters, the uncentered Kalman filters, they don't have much theoretical background. However, the cubature filters has much theoretical background, and it has been proved that they can cubature Kalman filter can perform better than the uncentered Kalman filter and so on. And 2010s onwards, as I told, the control over the networks plays a crucial role where like cyber physical systems or IoT based control and so on. And this is the classification of controls. So I have split this into three control techniques, mainly based upon the era. So the classical control techniques are basically the frequency domain control techniques where the design control techniques based upon the root lookers, body plots, and the classical PID controllers. So what I can say that 1950 and before, whatever the controls theory was developed, mainly in the frequency domain, we call it as a classical control. And in the modern controls, late 1950s or 1960s, when the emphasis was on state space methods, pole placement, LQR, LQG, and so on, we call it as the modern controls. And the postmodern controls, late 1980 onwards, where the robust control was dominated, we call it as a postmodern control. So this is one such classification. And the another classification, we can classify the control systems based upon the if the system and the control is linear, then we call it as linear control. For example, PID, LQR, LQG, and H infinity control. And non-linear control in general, if the plant is non-linear, then we call it as a whatever the control system we develop, we call it as non-linear. However, here the control itself can be non-linear as well. So so what I say here is if the control or the plant are non-linear, then we call it as non-linear control, which includes dynamic inversion or the Lyapunov-based controls like backstepping and so on, sliding mode control and so on. And the next one is the optimal control and the robust control. And this is the classification of the state estimators. We have seen some classical examples of the state estimators, some classical examples of the state estimators. So which includes the Leuenberger observer. In general, one can always ask what is the difference between the observer and the estimator. So philosophically, both observer and the estimators or the observers and the state estimates are the same. But in general, in the control systems community, the systems if the assumption is that they are not affected by noise or uncertain by some kind of external noise, we call it uh, as observer. Otherwise, we call it as the state estimators or filters. For example, the Leuenberger observer, which is the dual and the pole placement controller, while designing the controller, while designing the observer, we doesn't put any restrictions on the plant. We assume that the plant is nominal, x dot equal to x plus bu and y equal to c plus bu. We don't assume that some kind of uncertainty or noise like plus w terms or plus v terms in the state or output equations being added. Whereas Kalman filters or the filters or the state estimators are the one where the emphasis is on uh, the state estimation when the plant or the measurements are corrupted by noise. And these H infinity filters are bit the new as compared to the Kalman filters where the structure where the structure or the type of the uncertainty or the noise which is affecting the system is assumed to be of generic nature, whereas in the Kalman filter it is assumed to be the of Gaussian and so on. And once we say that when the plant is linear, then we can go for this linear estimators. When the plant is non-linear, then we can go for the extended version of the Kalman filters, which I told one can use the concept of Jacobians or the Taylor series, first order Taylor series approximations and so on. Extended Kalman filters, extended H-inverted filters, and their variants, and the sliding mode observers and so on. And this we have discussed the sigma point filters, uncentered Kalman filters, particle filters, cubature filters, and many more. So this is the classification, one such classification of state estimators. So briefly, I will go through this PID controller, pole placement, LQR, when to use and when not to use is will be the takeaway lessons from this discussion. Though I will not go much detail into the PID controller because this I will discuss while doing the hands-on session. So this is the fundamental, very simple or very basic PID control systems where this is a plant and the input is going to the plant, which is nothing but the output of the PID controller. The plant output has been compared with the reference, and whatever the error has been given, it has been given to the PID controller, which will provide the desired control input to the plant. So when I say the PID controller, it doesn't it is nothing but the proportional, integral, and the derivative control. What are they? We'll discuss in more in the hands-on session. And the conventional method is called as the Ziegler-Nichols tuning method. In the Ziegler-Nichols tuning method, we try to excite, we we break the feedback loop, and only the system is connected with the proportional controller, or the so-called only gain, and we keep on varying the gain unless we get the sustained oscillations in the output. And that gain for which we are getting the sustained oscillation is called as a critical gain. And that oscillations which we are getting, the time period of the oscillations, let's say it is a critical time. And based upon this critical gain and critical time, there are some standard formulas which will give us the Kp, K, and Kd. So that is the conventional Ziegler-Nichols shifting method, which will give us the first set of PID gains from which we can further fine tune based upon the thumb rules and so on. So another class of optimization methods, tuning things will be based upon optimization techniques like PSO, genetic algorithms, or Firefly, or so. But there are many new, heuristic methods one can use to find these gains. And as I told, once these gains are obtained, one can always use the fine tuning based upon the thumb rules. And what to do with the nonlinear system? So this is the big question. Big question. We will address this at the end of this lecture. And this is the pole placement controller. So, so the earlier one is basically a frequency domain controller, whereas this is the time domain controller. I assume that x dot equal to bx and y equal to cx plus du. I assume that d, or the direct feed forward effect on controls and output c, I assume it as a 0. And the assumption here is plan should be completely controllable and all states are measurable. And the control is unconstrained. That means I have infinite control is available for me to transfer a particular state from its initial condition to the final desired position, or final all state values. And the structure here is u equal to minus kx. You can see that x is coming from here. That means all the states are available here. That means if I have 300 states, I need 300 sensors. And this is minus k. How to find this gain is of much important is of much importance. And then u is nothing but u equal to minus kx. So here the objective is to place the closed loop poles at the desired locations. And if I substitute u equal to kx minus kx, then my closed loop system will look like this. Now my idea is I want to place the eigenvalues of a minus bx at the desired closed loop location. And so eventually it boils down to what should be the k value such that the closed loop poles equal to the desired poles. And when to use the pole placement controller? When the system is linear controllable, all states are measurable, and good information about desired pole location. How do you find the desired pole locations is a big question. That completely based upon the what kind of output response you want, what kind of damping you want for your system to for the closed loop damping, how it should look like, or how fast your closed loop system should behave. And these are all completely based upon the pole location. Suppose the farther you keep the pole away from the imaginary axis, then the systems will be very fast. You should not keep the poles very far away, because that means the bandwidth will be very high. And if the bandwidth is very high, there could be the two reasons. The first, it is not desirable. The first thing is, if the bandwidth is very high, then the high frequency components like noise will come into the picture, and it will excite your system. The second thing is, if bandwidth is very large, then you will need uh, more control for action, more control as well. The high control effort is also required. Whether your actuator can able to deal with the high control requirements. So these need to be taken care. And this LQR controller, the linear quadratic regulator. So the name, it is applicable to the linear system, and the quadratic is due to this cost function, which we try to minimize. And it is a regulator problem. In its naive form, it is a regulator problem. That means from any initial conditions, the aim of this controller is to bring the initial conditions to the 0. However, one can use, for the tracking problem, one can use the LQRI, linear quadratic regulator integrator problem, and which I am not discussing here. Here, the again u equal to minus kx is the one. The control structure is the same as that of the pole placement. However, what I am interested here is this q and r. This q and r are the tuning parameters, or the weighing functions which is required for the control calculations. This q and r basically tells about the emphasis, what emphasis you want to give. For the states, suppose if you want to, for example, you have 10 states, and if you assume that The third state is more important one, which I want to control effectively and so on. Generally, this Q will be, the Q is an n by n square matrix, where n is the total number of states. And in general, we assume it is a diagonal matrix. And for example, as I told, if it is the third element is the one which need to be put more emphasis, I'll put more weights on the third weight. And similarly for the control as well, if we want to put some more effort on some control channel, I will give the more weights to the particular channel in the R matrix. And how to find this Q and R is again based upon the problem at hand. One such techniques which is available in the literature is called as a Bryson's tool, through which one can always find a initial Q and R matrices which need to be further tuned based upon the application at hand. So when to use the LQR? When the plant is linear and controllable. If you don't know the desired pole locations where you want to place, then one can use this LQR. However, you should be knowing the Q and R, the emphasis which you want to give, which controls and which states is very much important. So that information is required. So the emphasis is on the states and or control limits. So the problem with both these state feedback and pole placement controller and LQR is it need complete state information. Suppose if I have 300 states, I need all the 300 state information. However, which is not desirable, or one may not want to use the complete state information. So the concept, whatever we have discussed in the first, this block diagram is valid for LQG controller, provided there are some changes. If this control techniques, whatever I'm using is LQR, and this estimator is Kalman filter, and I assume that the plant and the sensor now, this plant and this output is corrupted with the Gaussian noise, then I call it as the LQG. So it eliminates the assumption of LQR. So in the LQR, we assume that instead of the Y, all the states have been used, the X has been used. However, what you are using is from the limited number of states, which is the output, which I assume is the output, I could able to estimate the complete state vector, and that can be used for the control systems. And here the plant and sensors are corrupted by noise. So though I have not explicitly represented here, so it assumes that plant and the sensors are corrupted by noise, and emphasis is on optimality. And this is the block diagram for H infinity controllers. In the H infinity controller, the standard block diagram, what I say it as exogenous, this W is called as exogenous inputs, which may consider, which one can say it as, the reference inputs or the disturbances, all this I can lump into this W, and this Z is the regulated outputs, which I want to keep it, at specific level. I don't want them to go to infinity or so on. And this is the measured output. So from the sensor information, and this is the controller K, and this controller, whatever the output of this HMP controller has been given to the plant. So this is the basic HMP controller diagram, block diagram. But however, the aim here is to keep the transfer function, is to minimize the transfer function, or in specifically, we want to minimize the H infinity norm of the transfer function between this Z to the W. That means the regulated outputs, the effect of unwanted disturbances or all other exogenous inputs on the regulated output, which I want to minimize. In general, we assume that it is less than equal to gamma, where gamma is some uh, predefined value which can be find out from various, based upon the problem at hand. And when to use the HNP controller? Robust performance and robust application. Once, if we want the robust performance as well as robust performance means in the presence of all uncertainties, if I could able to get the desired performance, then I call it as the robust performance. And robust stabilization means if my system is stable for all kind of uncertainties, then I call it as the robust stabilization. That means if the plant has various uncertainties, then also if I could able to get the desired response, uh, if my aim is to get the desired response, then I can go for the HMP controller. And this dynamic inversion is another such control techniques. So with till now, what we discussed is basically the linear controls or the linear state estimators, where I assumed that my x dot equal to ax plus bu, where a and b are the constant matrices. If those A and B matrices are function of states, then I can represent them as x equal to fx plus gx into u. where fx and gx are nonlinear systems. So if I choose this control law, it's something like this: u equal to g inverse x into x dot minus fx. If I substitute this u here, then g terms will get cancelled and f terms will also get cancelled. Then you are only left over with x dot equal to x dot. But that is not what I want. So now what I want to do here is my x, I want to drive it to the x desired, or in a long term, what I want to say that my x and the x desired, that means desired state should be equal to the desired state, and my plant state should be the same. So instead of this x dot, if I replace with x desired, and if I substitute this u here, then what will happen is x dot equal to x desired dot. The problem here is we should know the inversion of the nonlinear dynamics. So since we are inverting this G inverse X, we should have the good information about this G matrix. The second thing is, if this G is non-square, then how to do this one? There are various ad hoc methods to calculate G inverse when the G is not non-zero. One such method is one can use the concept of pseudo inverse to calculate this G inverse for the non-square matrices and so on. And here the concept here is it cancels the non-linearities and replace it with desirable dynamics. So whatever this x desired, if you say it is a linear dynamics, for example, x dot equal to minus a into x, where a is a stable system matrix, then what we are saying that it cancels the non-linearities and replaces with the desirable one. And now it boils down to there will be basically two loops. One loop is to cancel the non-linearities, and the second loop is for the so-called new transformed linear system, and then we can design the linear control systems is much more understood by the control engineers, and then one can design. So there are two loops again. That linear control itself can be a robust control like H infinity or mu synthesis controller or so on. So this particular approach is called as a dynamic inversion, and much research has been done again in the aerospace community, where in the NASA the people have explored this, NASA and so many other space agencies as well. So this is the summary of my control design. The PID controller is simple. Only three gains are required: KP, KI, KD. Very tedious process for multi-input, multi-output system. And when we say that how to apply for the nonlinear system, this I have not discussed in the details, so let me throw some light on this one. So generally, as I told that most of the plants are non-linear, or the plants need to operate in the complete, whole operating region. So what is the standard process is they try to split the complete operating region into small parts, and they assume that, and they are so called as operating points, where your linear plant non-linear plant can be linearized around that operating point. And for those operating points, we design the PID controller. And if your system is acting in between those operating points, then we had to do the scheduling or the interpolation of the gains, which is called as gain scheduling. So here, the complete idea is to split the complete nonlinear operating region into few operating points. How The big question is, how do you define this operating point? That is very difficult one. And how to choose this one? So you should have the complete information about the system. Uh, for example, if it is a DC motor, then I can say that for a small for a one set of PID controller will work for 0 to 500 RPM, 500 to 1000. Another set of controllers is required, 1000 to 1500. Another controller is required, and so on. So what I'm saying that lots of controllers are required if you want to complete design the operating system or the controller for the complete nonlinear operating range. And one has to do the tedious gain scheduling is required for the if you want to apply the PID control for the nonlinear system. So not only PID control, any such linear controller, it has to go through the tedious gain scheduling. However, one can avoid if your controller can take care of all kind of uncertainties which you encounter through all the operating points through one controller, then it is possible to go with one such controller, but hardly it is possible. Another one is pole placement, the full state feedback control. Good to design when desired pole locations are known. LQR, then easy to design for MIMO systems, low pole placement also, and the emphasis is on optimal and state estimation, state optimal state in control. And LQG, when only limited states are measurable, then as we told, it can be combined with Kalman filter, which is an state estimator. And the H infinity controller, its emphasis is on robust performance and stabilization, and the dynamic inversion for the nonlinear systems. Next, I will go to briefly to the state estimators. I will start, though it has lots of equations. I will not go into much details into the equations. Just I will tell you the philosophy of the Kalman filter. So this is the discrete system. So this is xk and yk. We have seen x dot. So x dot can be, can be converted to the discrete system or discretized version by using Euler's approximation. So there are many discretization methods are available. So here, whatever the Kalman filter I am discussing is the discrete for the discrete systems, where the xk, you can see that these two are A and B and C are the discretized ABCD matrices, which one does not need to much worry about these things. But the important thing is these two noise, WK and VK. This WK is called as a process noise, which is affecting the state. This process noise could be, one can combine all such uncertainty, non-linearities, and so on, which can be observed in this process noise. Similarly, for the measurement noise, if this is basically the sensor noise. And the Kalman filter is a two-stage process, the prediction and update. In the prediction, what we do is we try to predict how my state will look like without having the output information. Once the output information is with us, we try to combine with the predicted value to get the updated state. So some of the things which are required to initialize the Kalman filter is they are the initial state, initial covariance, control input, the output from the sensors, and Q and R. Q and R are the noise covariance matrices. Q is the covariance matrix for this WK, and this R is the covariance matrix for this VK. So more specifically, we assume, as far as the Kalman filter is concerned, we assume that this noise or random noise is of Gaussian nature. And in the prediction step, what we are trying to do is k at k minus 1. That means we have the information till k minus 1, and based upon the k minus 1, we try to predict the k. For example, if we want to predict k equal to 1, let us assume it is a time step, then we should have the information of, if I substitute k equal to 1, this will become 0. So, so if I substitute k equal to 1 here, what is happening? A is known to us, B is known to us. This 1 minus 1 and 1 minus 1. So this k x hat 0 at 0. So how, for the first step, how I'm getting this x 0 at 0? I'm getting from this initial, which is known to us. And although this UK is also known to us by Q and R. So then I'm trying to predict the covariance. So for the covariance, what I want to say is, again, if I substitute, if I want to start with k equal to 1, then since this initial covariance is known, then I will use it here, and Q is known. So based upon this, what I'm trying to get here is, I could able to get the predicted state and the predicted covariance. The predicted state means I am trying to predict how my state will be at k equal to 1 based upon the information at k equal to 0. In the update stage, that means once I have this measurement information, I try to update the predicted value. So you can see that, you can see that this predicted value, which is coming from here, the predicted covariance which is coming from here, this y is known to us and r is known to us. So I'm trying to combine the predicted value along with the outputs to calculate the updated. So what I mean by updated means x1 at 1. So this is nothing but the updated state at k equal to 1. Similarly, the updated covariance also I can calculate based upon this predicted one and so on. So for the next time step, when k equal to 2, that means I have the information x1 at 1 and p 1 at 1. So this is 1 at 1 and 1 at 1. So when k equal to 2, then what is going to happen is x hat 2 at 1. So this will become 1 and 1, 1 at 1. So 1 at 1, how did you get? From the previous iteration. So previous iteration, we have seen that we have that 1 at 1. So that information I will be keep on using here. So it is kind of a recursive process. Prediction, update, and update prediction. It will keep on repeating until the complete procedure, until this k, once it reaches the maximum values of k or the time step. And this is another H infinity filter. So what is happening in the H infinity filter is, here instead of what the assumption has been assumed in the Kalman filter is that the process and measurement noise is Gaussian. However, here that assumption has not been considered for the HNFT controller design. So this is the cost function which one has to minimize. So in the cost function, this is basically game theory cost function, which I will not go much into details. So here the philosophy is to keep the supremum or the maximum value of J infinity less than gamma. And this gamma can be tunable gamma. This can be dependent on this QK and RK. Note that this QK, RK, and P naught are not the covariance matrices. These are the tuning matrices. And whereas in the earlier cases, these are the covariance matrices of the Gaussian process noise and Gaussian measurement noise. However, here this QK and RK are just the tuning matrices. And so here the whole philosophy is to keep the maximum value of J infinity less than gamma. So the remaining derivation part, it is very much similar to the Kalman filter. However, the philosophically how it is defined that in the HNP filter, we do not assume uh, any type of assumption on the noise. So this works for the generic noise. So it can work for Gaussian noise, non-Gaussian noise, or any such kind of noise. So, though the two estimators what we discussed, the Kalman filter and HNT filter is being developed only for linear systems. However, they can able to one can extend those the so-called extended Kalman filters and extended HNT filters for the nonlinear system. However, the problem here is we are assuming that the higher order terms are zero. So, in a way, if the system is highly nonlinear, that means when there is some significant information is hidden in the higher order terms, then in the EKF or EH infinity filter, which we are assuming it is a zero, then your estimation error, then the estimation error may be very large and the convergence is not possible. So the Quadrature Kalman filter is one such non-linear filter. One can is the prediction and update. So this F is a non-linear. This W again has been here assumed it as a Gaussian, and VK is also assumed as a non-Gaussian. This F and H are the non-linear functions. So the prediction and updates is what we have seen in the Kalman filter and so on. The structure will be the same. The prediction and the process will be the same. However, how do you calculate this predicted or the updated state is of much importance. So there, what we assume that based upon the A, B, C, D matrices or the Jacobians of F, Jacobians of H, which are nothing but A Jacobian and B Jacobian for the nonlinear systems. However, here instead of using the Jacobian approach, what is happening here is we are trying to calculate the end integrand by using the nonlinear function. So these four things can be boiled down to the integrants of the form nonlinear function into Gaussian function. So the heart of this particular Quadrature Kalman filter is how do you find the integrants of nonlinear function into Gaussian function. So this is the one such approximation which is called as the Quadrature rule. So this is very fine. So if you substitute this here, then you can able to get the predicted state predicted covariance, updated state and updated covariance. But but what will happen if this assumption of this Gaussian noise and Gaussian process and Gaussian measurement noise is not valid? Then what one has to do? Then then this in its naive form, this Kalman filter may not work. Or if the measurements are from multiple sensors, if you want to use the multiple sensor fusion, that means if the measurements are available from multiple sensors, then how to fuse that one is also of much interest in the control community. And then one has to go for the Quadrature information filters or the Quadrature HMPT filters, which we have extensively worked in the last 1 decade in this particular area. So I will not go into much mathematical aspects. So what we are having here is we assume that we have the measurements from d number of sensors for a particular state vector. So then we can use simply by using this summation, where this y is the inverse of the covariance, and the small y is the information vector, which is nothing but the product of this covariance into x. And the important thing is this P inverse should exist. In general, P inverse will exist if you assume that if there is some small uncertainty in the plant as well, the uncertainty could be whatever be the small, then P inverse will exist. Otherwise, there are some ad hoc mechanisms when P inverse is very close to, if if to the singularity, then how to deal with it. There are certain methods. And the square root versions are for the numerical stability. So this is one such way to avoid, the singularity in the P. One can use the square root version, and one can refer this reference for more information on cubature information filter. So this particular cubation information will deal with the measurements from multiple sensors. However, again, we have not yet addressed if the noise is Gaussian. So that can be, so what we can see that if we combine the cubature Kalman filter plus HNL filter, the good properties of the cubature Kalman filter is that it can directly able to deal with nonlinear systems without using any assumptions, linearized assumptions. And the good thing about this HNL filter is that it can able to deal with non-Gaussians or any unknown noise. So if we combine both of them, then CHF, Cubager H infinity filter, has the properties that it can able to deal with nonlinear systems as well as the systems which are affected with unknown noises of any kind of distribution, whether it could be Gaussian or deterministic or so on. And however, this so in this approach, what we are doing here is here it does not deal with multiple sensors. If the information is coming from multiple sensors, what to do we don't know. So this cubature H-infinity information filter, what we are trying to do here is we are trying to combine the concepts of cubature Kalman filter. That means for the nonlinear systems, that means for any kind of noise by using H-infinity filter, and for multiple sensors. So this cubature H-infinity filter, if your system is nonlinear and if the noise is non-Gaussian and if the multiple sensors, then one can go with this cubature H-infinity filter. So this is the summary of the state estimator. One can see here, if the Kalman filter is linear and Gaussian, go for H infinity. If it is non-Gaussian, go for the H infinity filter, Gaussian or non-Gaussian, anything. Cubature filter with nonlinear systems is Gaussian. Cubature information systems, nonlinear systems with Gaussian noise with multiple sensors. And if you assume that your the system is nonlinear as well as you want it to work fine for Gaussian as well as non-Gaussian noise. And further, if you have the information from multiple sensors, then you can use this cubature H infinity filters, cubature H infinity information filters for multiple sensors or so. So that tells about some of the recent trends in past and present controls, but we'll see what is the future of the controls. So this is one such unmanned marine vehicle. So where one has to autonomous navigation is required for this unmanned marine vehicle, where it has to navigate in thousands of kilometers from the sea. So then what a simple method for the navigation, the propeller or the fuel which is required, the fuel which is required for this one, either one can store a tons of fuel required, diesel or whatever may the fuel required for this particular 1,000 kilometers, you know, operation. That is one way. The second way, if I want to operate for 1,000 kilometers, then what I will do is I will connect to 1,000 kilometers wire, and I will keep on continuously providing the supply. The both of them are not the viable solution. So one such solution is if I use the combination of solar, wind, and uh, and diesel for emergency, then I can use this for the autonomous navigation. But controls is required in this one as well. So it has to withstand the optimal control need to be used. The control allocation need to be used in an optimal way. For example, when to use from the solar, when to use from the wind, and when to use diesel. The second thing is during on the highways, how to stabilize this particular enduro is itself is a big question. So there the control plays a crucial role, and the Indian naval and some of the naval agencies they are very much interested in this kind of its control development for this kind of vehicles. Another such vehicle is the AUSC Autonomous Undersea System Institute vehicle. So this is completely based upon the solar energy, solar panels itself, and it has some amount of diesel as well for the emergency. So these are some of the challenging applications one can look into for its renewable energy applications, renewable energy and the control applications. And as far as the future controls are concerned, there are many approaches, many control techniques are required. As I discussed, if you want to, if the system is very complex, then modeling itself is a big challenge, like traffic congestion or air traffic control. And the next thing is communication over network. So where we need the expertise from cloud computing or big data analytics or machine learning, where where the internet where interconnection is between the internet, actuators, sensors, processors, which is so-called IoT based control. And security and privacy is also very much is playing a crucial role, is very much required. And fault tolerant controls, which includes the fault detection, isolation, and control design. What will happen if some of your sensors or actuators are faulty? Then can you able to recover the desired performance or the nominal performance, even in the presence of the faults, is also of much interest. And the human in loop applications, when the human is involved in some of the applications, how do you ensure the safety of the human is very much required. And the smart vary grids, so the so-called as super grids, with the combination of AC and DC grids, how to synchronize them, and that is also crucial role. Smart cities, stock market control, fully autonomous vehicles. Now everybody, all the automotive industry is, whether it will be Mahindra or the service providers like Uber or Ola, everyone is interested in the autonomous vehicles. So there also control plays a crucial role. And for the healthcare, for example, diabetics control, cancer, Parkinson, and so on, there also control is very much required. Though trials, though many ad hoc methods have been proposed for dealing this the so-called feedback control of diabetics and cancer and Parkinson, but it's not been still is not available to the common man. And the COVID-19, how do you this COVID-19 is another such interesting application of the control. So where one can the lockdown period can be decided based upon the various optimal control strategies, where which is based upon, for example, the total number of deaths, total number of infected, total number of susceptible SIR model, and so on. So the researchers are working, very closely, mainly in the France, sorry, mainly in the US and Italy, and the remaining parts of the world are also now they have started, they are trying to combine the control concepts to come up with some solutions for the COVID as well. So we have discussed various control systems, various state estimators, past and present controls, and the future aspects. And this is one such reference which I would like you to refer for various future aspects of the control. Now we will go to the PID control design using MATLAB. So this is the standard PID controller. So what I will say that the output of the PID controller has three different terms. So the proportional, mainly if the control input is proportional to the error, we call it as a proportional controller. If the control input is proportional to the integral of the error, we call it as an integral control. If the control is proportional to the derivative of the error, we call it as a derivative control. And the proportionality constant we can replace with Kp, Ki, Kd, and we are combining those three, proportional, integral, and derivative. We call it as a PID control. And this is the Laplace domain, Laplace or S domain one. So the three gains which are of much importance is proportional, integral, and derivative, Kp, Ki, Kd. So finding, tuning the controller or finding the PID controller, designing the PID controller is nothing but finding an appropriate set of Kp, Ki, Kd values to achieve the desired response. So in the proportional controller, we assume that Ki and Kd are zero. So this is the same thing. So the benefit is it improves the rise time, but the limitation is it couldn't able to deal with the steady state error. Unless if your plant has inherent integral action, then we cannot then we can go for the proportional control. Otherwise, it will not ensure the steady state error. We'll see this in detail. And in the proportional controller error, you can see that derivative term is zero, where has proportional integral. So if you use in general, the integral eliminates the steady state error, but it has, the sluggish control response builder. So slowly the control will build up. However, we can use the combination of PI control, so which improves the rise time and zero steady state error. So just for your information, 90% or 95% cases of in the industry, the basic controller or the control systems, what they use is a PID controller. And among that 95% cases, one only go for PI controller. They don't use the derivative controls due to the practical reasons. So, so the derivative controller, so PD controller here, Ki is zero. So it tries to predict the linear prediction of the future errors. It improves the closed loop stability. But for the physical realization, instead of the direct derivative terms, we use this particular approximation. And PD controllers improve stability and faster response. But but it has its own problem. When the derivative is coming to the picture, it amplifies the noise. So one should always avoid this derivative control due to the two reasons. We are trying to approximate this derivative control with this physics for the physical realization. This one, and the second one is it amplifies the noise. So so when it is not required, when we can able to achieve the desired response with PI controller, don't go for the derivative control. And the derivative control uh, combines the benefit of proportional. That means improved rise time, integral steady state error to zero, and derivative control improves stability. So this is one such plant. What I mean to say that this is a plant, GS equal to 1 by S into S plus 5. The important thing to observe here is that plant itself has inherent integral action. And this is the open block diagram, and we'll try to analyze what is happening using the symbol. And this is the symboling diagram. So this is the open loop control. Just I have given input as 1, and the output you can see that it is continuously increasing. So now what I have done is I use the gain controller, only the gain. So what the output has been fed back, and it has been compared with the reference to generate error and this gain k value. This gain I assumed it as a 10, and you can see that very nice property. So you can see that it is settling almost in 2 seconds, and the overshoot is also not more than I think 2% or so. This is very good. So by using only gain control, I can able to find the steady state error as well zero. But the good thing about this is the plant has inherent integral action. You can see that 1 by S is here. However, as soon as if I take the new control, new plant, where I have added this 1 in the denominator, that means the good property, this is the type 1. So there is one integral action integrator in the plant. As soon as this property has been lost due to whatever your plant is if it is in this form, which is the key difference, then we are going to see what is going to happen. You can see the control, everything is the same, the left one and the right one. But the left one is the one with the inherent integral action 1 by S. You can separate this 1 by S here, but you cannot separate directly. So if I use the same gain controller, you can at first instant, both of them look very much similar. The left plot and the right plot will look very much similar. However, the important thing to note here is that it is settling at 0.9, whereas it is perfectly the steady state error is 0. This is due to the fact that integral action is coming into the picture. However, here you can see that uh, though all the remaining specifications are very much similar to this one, but the steady state error is not 0. That means I want this output to go to 1, but it is settling at 0.9. That means 10%, around 10% settling uh, steady state error. So 10% steady state error. So here, sorry, I might have spelled it wrong. So it is the steady state error here is 0. However, steady state error here is not 0. So the reason why here is the plant does not have the inherent integral action, whereas here the plant has integral action. So that's why here the integral control is not required. However, for this, since the integral action is not there inherent in the plant, and neither we are using nor we are using the PI controller, so that's why the steady state error is not bound to 0. So next, what we'll see here is if we design the PID controller, where I will try to have both the integral and the derivative control, and I will see what will be the desired response. So this is the same plant, the new plant, so-called, where there is no inherent integral mechanism is there in the plant. I have used 3 cases. The first case is proportional controller with 10. Integral and derivative I have assumed is that this case we have seen that there is steady state error of 10%. Then in the next case, I have used the integral action. And the third case, I have used the derivative action as well. So these are the different plots. I will not go much into these plots. However, I am much interested in the summary of this one. You can see that the summary, as far as the summary is concerned, if I use only the proportional controller, you can see that rise time is good, peak overshoot is good, settling time is also good, but the steady state error. If your aim is to reduce the steady state, if you want the steady state error to go to 0, then this is not the viable solution. Otherwise, proportional controller is very simple controller. Only one controller is required. It has the remaining time domain properties are very nice. As soon as I use the integral control, PI controller, you can see that the steady state error has been vanished. However, there is some slight sluggishness due to this integral action. That means settling time is more, and you can see that the overshoot is also more, very high. There is not much difference in the rise time here. And when I use the PID controller, so the derivative term is also coming into the picture. Just I'm showing you the time domain response. So there is an improvement in the rise time and little slight improvement in the peak overshoot. And whereas again there is some improvement in the settling time and the steady state error is zero. However, this improvement is not much as compared to the PI controller. So for the practical reasons, I will go with PI controller with ESS as zero. The big question here is one can ask how I have how I have got these values. KP is 10, 5, 10, 5, 20, and so on. Is it just randomly I have selected to this one? So the answer is no. It need a lot of tunings, and there are hundreds of methods available in the literature. And I think all the researchers who want to work with the fundamental control or who have just started the fundamental control system design or who are expertise in the control system design as well, they should be aware of this standard auto tuning method. By using 1 minute, one can get the KPKKD value. The so-called Ziegler-Nichols tuning method is fine, which need a lot of tuning. The so-called, you might have come across in the papers like bacteria foraging method for PID controller tuning or the particle swarm optimization or so on. So there are hundreds of methods. But what I can say that those methods in 99% cases are not required to find the KPKKD value. As far as the research publications are concerned, yes, it is required. However, frankly, let me tell you the control perspective of using the so-called heuristic methods for the controller design is no control engineer or no control researchers nowadays they're not appreciating this so-called the standard. If you find some new new optimization algorithm combined with the control some control finding the PI values, PI, KP, KD values by using that optimization method. And if you want to publish in a good control journal, then outright it will be rejected because it has been saturated. That area has been completely saturated. So if you want to pursue the good research in that one, please don't go for that one. However, if your plant or the control needs some KPK, KD values, then one such method, what I'm going to show here is, it will work in 90 to 95% cases. So which don't need much, complex heuristic optimization algorithm. By using, the standard 1 minute method, you can able to tune that one. And for the simplicity, I have used the simple DC motor transfer function where the speed is the output and the voltage is the input. The plant parameters is something like this. And my desired specification is cycling time should be less than 0.5 second, overshoot should be less than 5%, peak overshoot in the steady state error should be less than 1%. This I have taken from this Michigan University website, this particular transfer function. These are the parameters so which you can directly write the MATLAB. And this is the open loop response. So you can see that this the same transfer function what you are seeing here is I have implemented using the MATLAB. This is the state space model, which is not much required now. So you can see that it is an open loop control, I want it to go to 1. So if the reference input is 1 to this one, and actually the plant input is 1, and the output, you can see that this is the output. So the problem here is this looks very smooth one. So there is no overshoot, very good. And the settling time is around, around something around between 2 to 3. The rise time is also fine. However, you can see that the steady state error, it is 0.1. So 90% steady state error. I want it to go to 1. So the desired specification has not been met. And now I will show you how to uh, use this PID controller. This I will demonstrate how to do this tuning. But just please see this one. If I use the PID controller, then I can see that all the specification have been met. The rise time is very fast. You can see that very fast it is going from 0 to 1. And settling time is also very small. It has settled very fastly. And overshoot is also very less. So if I zoom, this is from 0 to 10 seconds. If I zoom this particular value from 0 to 1, then this is the equivalent response. More specifically, if If I compare these two things, open loop and the closed loop, so this is of much interest. This table. So rise time is greater than 1 with the PID converter is 0.06. Peak overshoot is less, and in this case it is 4%, so which is fine because it is in the desired specification, which is uh, less than 5. And my settling time is 0.4 and the steady state error is 0. The, the question one can ask here is, what is this PID value and how did I receive this? How did I obtain this PID value? This now I'm going to show in 1 minute. So this is the demo what I'm going to show you. So this, what I will show here is, this is my plant. You can see that the coefficient K is my numerator, J into L, Rj plus BL is the S to the power of 1 coefficient, and this is the constant. This, then if I, so this, if I, yeah, so this is the DC motor and this is the PID controller. So what I'm going to show you here is, as soon as if you take the PID block from here, if you just type here from this Simulink library, if you enter PID block, you will get this PID block. So suppose if I want PID block here, so this is the PID block, what you can see here. So this is the standard PID block. Yeah, this is the PID block. If I double click this PID block, by default values are 1, 1, and 0. So the proportional value controller is 1, proportional gain is 1, integral gain is 1, and derivative gain is 0. And this filter coefficient, what I have discussed for the physical realization of the derivative one, it has been assumed as 100. So now we will see, if I use this PI controller, and if I run this one, the nominal or the default PID controller, then you can see that it is running fine. But the problem here is, you can see that I ran for 10 seconds. You can see that still the system has not settled, it's still going and going. We don't know what is happening until we run for 100 or 1000 seconds. So obviously this is not satisfied the desired specifications. Now I will show you in 1 minute how to tune this PID control. This is very much important. The step number 1 here is double click the PID controller, and there is this small button here which is called as tune. If you press this tune, then you can see this. As soon as if you press this tune button, it will show you the response like this. Whereas this dotted line is the block response, just now what we have seen. And this one is the tuned response. The dark blue line is the tuned response. Now I will tell you how to get this response and what are the KPK, KD values. What you have to do here is, you click this show parameters, whatever you are seeing here is, it will show you the KPK, KD values. And this is the block. So the nominal one, what we have seen, the default values of the PID 110. If we change it to 18, 51, and 0.95, then these are the desired rise time. These are the closed loop rise time, settling time, overshoot, and so on. So you can see that the overshoot is 7 and so on. However, this is the first such, control design what the MATLAB auto tune will automatically tune. But one thing to observe here, that it is not, these tuned values are not the one, the tuned after using this PID controller. Whatever you are getting, the rise time, settling time, overshoot are not the desired one, because the overshoot is very large. I want less than 5, and similarly the settling time also I need faster. So what I'm going to do here is, I'll close this one, and you can see there are two slider gains here. The first one, the top, I'm not sure whether it is visible or not. The top one is for the response, and the second one is for the robustness or the transient behavior. You can see how the parameters, if I want the faster response, now you can see that the settling time is 1.5. I want faster, so what I will do is, I will slightly change this one. This is dynamic one. As soon as if I'm keep on changing, you can see that now settling time has come down to 0.3. But you can see that if the settling time has been reduced, but the overshoot has gone to 10%, 10.7%. Now what I will do here is, to transient behavior, if I want to control, I will use the lower slide button. So what you can see that, so if I am keep on going on the left side, then system is becoming more aggressive. So and the overshoot has been increased. So what I will do is, I will keep on moving this gain to the right hand side, further right, you can see the corresponding change in the overshoot. You can see that the overshoot is now 4%. The settling time is 0.5 and the rise time is 0.008. And obviously you can see that system has reached the steady state. So the steady state error is zero. So now the corresponding PID values are 141, 389 and 10. And this is the filter gain. So now I don't want to manually type this in the PID control block. So if I use these values in the PID control block, then this is the response what I am getting. So now what I will do here is I will just click this update button. As soon as I click the update button, then what you can see here is then all the parameters has been updated automatically here. And now simply I will press OK and then I will use this and then I will get this desired response. You can see the desired response. Though it is for 10 seconds, if I want to see only for 1 second, I will do this one and you can see that the nice properties. So how much time it takes to run this one? If you have this block diagram ready, only 1 minute. Again, I will explain you in 1 minute what you have to do. Double click this PID block. By default, it is 110. Since I have tuned this one, some values are appearing. Click this tuner button, and tuner button will show something like this. So since and then show parameters, and you keep on using this particular block. If you want to change the some of the steady state parameters and so on, so you keep on change for the faster response, like settling time and steady state error. You keep on increasing the top gain. If you want the transient response to be controlled, like the peak overshoot and so on, you try to use this lower slider gain. And automatically it is a dynamic thing, and you can see automatically the corresponding PID values and the corresponding you know rise time, settling time, and overshoot. So it hardly takes 1 minute to tune the PID controller. This auto tuning method works in 95%, 90 to 95% cases. In 5% cases, it doesn't work. Then what you have to do is you have to use the standard, Ziegler-Nichols method or so on. So this is the demo what I want to show you, and these are some of the collaborators with whom I have collaborated in the last 1.5 decades, with whom I have published at least one paper, and still I am in touch with them, and I am collaborating with them. Uh, some are from the industry, some are from the academia, and so 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 these are the collaborators, And I would like to thank the sponsors who have sponsored my research in the past 1.5 decades, which includes the MHRD and UKRI, UK India Education Research Institute initiative, and the special thanks to Airbus for EU FP7 project. As part of the EU FP7, they have funded me, and Vikram Sarabhai Space Center, with whom I am currently associated in terms of the sponsored project from them, and Department of Science and Technology, who has funded for me for for the various real applications of for the control systems by using OpenRT and so on. And thank you. And sorry that I have taken a bit more time than the time allotted to me. Now I'm open for the questions.
Thank you, Dr. Bharani. It was really an informative session. Um, there are quite a few questions. So shall I start asking them?
Yes, please. Yes, yes, yes.
Okay. So the first question was from Mr. Srihari. Sir, can we model entire electrical system with using these KVL, KCL law or by using system identification?
We cannot combinedly, we cannot we cannot model the complete systems by KVL or KCL. It is not at all possible. So the idea here is to use the system identification. Yes, by using the concept of system identification, you can identify the linear models of the complete electrical system. However, one has to again ensure that the single system, whatever you have obtained, either it could be the state space model, or it could be the transfer function model, or in some cases you can estimate, you can identify the nonlinear models as well. So there, one such model may not be sufficient to for the complete electrical system. What one can do is, as I told, various try to use the various operating points. Try to first of all find what are the different operating points required, and based upon that operating points, try to give different kinds of inputs required for the system. At the same time, try to excite the system for various kinds of uh, frequency signals. Not you should not only but first of all you have to see what kind of frequency modes your system will experience. Based upon that, you have to excite the system with the corresponding frequency domain signals, the combination of frequency and time domain signals, chirp signals, and so on, and then you can identify the systems. Yes, it is possible to identify the complex electrical systems, not only electrical systems, the complex systems, whether it could be anything. So we have some experience in finding the very complex methods. Generally, people go for the CFD models or some finite element models for to analyze or for some system modeling. However, we have used the system identification tool to find out the linearized systems or the so-called transfer functions for various operating regions, and up to 99% match one can we can test by using the system identification toolbox in the MATLAB. We can even test how we can even able to know how close your identified system is. And in that particular case, for it is for the ramjet very complex combustion missile model, we could able to get 99% accuracy as well. The identified model using the system identification and the nonlinear model. You can, if you want more details, you can refer my 2019 paper AIAA Journal of Propulsion Power for that one. Yes, it is possible.
Okay. Then the next question is there any other method better than Signal-Nichols for PID? Can you suggest some method similar and accurate than this? So I think one it might be the demo which you had shown. Is there any other methods that you may suggest?
Yeah, there are the demo which I shown is nobody knows what the algorithm is running behind that one. Only the MATLAB knows that what is the exact algorithm what they are running. So MATLAB, what they're completely MathWorks, they completely keep on working on the optimized way to get this KP, KD values. If it is a constraint control or what, so no one knows what exact algorithm is running behind this MATLAB tuner. But there are some methods one can always use. For example, one can use the concept of because this whatever the method whatever we have seen, not explicitly we have not yet tested for the parametric uncertainties. Suppose if the plant parameter varies, if whatever the plant we have seen are A, LA, and so on, if it is varies with respect to the time, whether the controller what you have designed, whether it will ensure the robustness or not. But during those consideration, if you want to have the so-called robust PID controllers to deal with parametric uncertainties, one can design these KP, KD values by combining the concept of H infinity controller. That is one such method. The second method is one can use the concept of Khariknov's theorem. They can find out the Khariknov's based PID controller as well, which will ensure that your plant will give the stabilized PID controller whatever you have designed will give the desired response even in the presence of the uncertainty. So these are the two such approaches one can use to find the PID controller to deal with parametric uncertainties and so on.
Okay, thank you. Next question is whether the prediction stage of Kalman filter should satisfy the observability and the controllability condition.
Uh, as far as the estimated design is concerned, there is no need to find the controllability because one can always treat the controller and the estimated problem as two different problems, and one can design the controller and observer independently. This is the so-called the separation principle or the certainty equivalence principle. What it says that I can design the stable controller and I can design the stable estimator, and when I combine both of them for the linear system, it will give a stable closed loop response. As far as the prediction stage is concerned, if you see the prediction stage does not require the output information. So y equal to c into x whatever you are seeing. Only the update stage required the C matrix or output information. So as far as the prediction stage is concerned, it does not need to satisfy the observability condition. And it does not need to satisfy the controllability condition. Controllability condition is not required for the estimated design. That is my answer.
Okay. Then, can you explain at what point Kalman filter design fails, and is there any limit of Gaussian noise for design while doing the simulation?
There are two cases which we have encountered where the normal Kalman filter fails. The first one is if you try to implement the normal Kalman filter or the extended Kalman filter to the highly nonlinear systems. For example, if you consider a very simple case of autonomous vehicle, where one has to turn very severely, when there is a severe turn, when the trajectory has a severe, turning angle, then during those cases, the Kalman filter error will be very large. And if that is very steep, if that angle is very steep or very sharp, then the Kalman filter in general fails for the very complex nonlinear autonomous vehicles. So that is one thing. And is there any limit of Gaussian noise for design? Yes, the Kalman filter has its own limitation. That means it assumes that the process noise or the Gaussian noise. Somebody is unmuted. Yeah, okay. So the Kalman filter itself, it assumes that the process, while for the design, the process noise and the Gaussian noise is, the process noise and the measurement noise is Gaussian. If due to some particular case, due to some particular scenario, if that assumption is not being satisfied, then the Kalman filter will not work. So in some cases, the heavy-tailed Gaussian noise is possible in some seekers or in some cases of radars, where the Gaussian distribution will not, where the noise distribution will not follow the exactly normal or Gaussian distribution. During those cases, one cannot guarantee the Kalman filter, the effectiveness of the Kalman filter. Then one has to go for the HFT filter also, or the particle filters, in to be more specific.
Okay. Then, next, which type of control and what type of filter is good for state estimation in power system?
Okay, so as far as the power system is concerned, if you see two area systems or hydro power, hydroelectric power plant, or or any of the power systems, the fundamental control, what if you see the Kundu test book, which is being referred by many of the researchers in the power system, he has used only integral control to achieve the desired performance for the two area systems, or it can be extended to the any area systems as well. However, it does not guarantee the steady state error is going to the zero in that particular case, but uh, but but the transient response was very poor, so one has to go for the PID control. As far as the simple power systems are concerned, that depends upon what kind of power systems you are dealing. If your power system, if it is in a very naive form, very nominal form, then yes, PID controller and normal Kalman filter will work. However, as soon as the more non-linearities are coming to the picture, nowadays, if you use the so-called the smart grid, or so-called, if you are getting the information, the sensor information from PMUs, or from various satellites or so on, where the synchronization is very much required, then the standard PID controller may not yield the good results. Depends upon what kind of power system you want to operate. Is your power system is prone to faults, then you have to go for the fault tolerant control. If your power systems need the transmission over the network or through the Wi-Fi or through satellite communication, then then in its then the best estimator one has to go for is sigma point filter. Don't completely rely on the normal command filter. Sigma point filters or the particle filters. And again, if you have some restrictions on the computational complexity, that you don't want to go for very high computational processing, then you, instead of the particle filter, try to go for the unscented Kalman filter or the curvature Kalman filter. So what I can say, that based upon the power system at your hand, you can start with P controller, PI controller, PID controller, the simple power system. If it is much more demanding power system, very highly nonlinear power systems, where it is prone to faults, then one such viable alternative is
sliding mode controller, which has the capability to deal with the faults as well as uncertainties as well. And if you want, if your system is highly nonlinear, then go for the uncentered Kalman filters or Kubacher Kalman filters or particle filters. So that is my answer to this one.
Um, the next question is, can you tell about ADRC control and how PD and PID are implemented in ADRC?
I don't know what is this ADRC. I don't know what is the abbreviation of ADRC.
Um, yeah, even I was not aware. I just Googled it up, and so it is active disturbance rejection control. And the question was asked by Prashant, Mr. Prashant.
Mhm.
Okay.
Okay, active disturbance rejection control. I am not very much aware of this one, but let me whatever I could what I could say about this active disturbance rejection control. That means so here what one want to the purpose here is to cancel out the control actively. So that's what I can say that for that particular, if you want, suppose if your control parameter should vary based upon the magnitude of the disturbance or the frequency of the disturbance and so on. So one can use the adaptive control for that one. And how PD and PID are implemented in ADRC. So one such, they can be implemented provided your PD or PID like KP, KI, KD values are not the constant one. So if you can include some adaptive mechanism which will ensure that your KP, KI, KD will change or will vary in an optimal way to handle the disturbance, or in another way you can find out you can come up with the optimization function where you want to minimize the effect of disturbance on the output. So what I can say is that if you can come up with the optimization function where you are optimized where your objective function is to minimize the error which is basically due to the disturbance, then you can go for this adaptive mechanism where KPKI and KD values can vary with respect to the disturbance. And the second thing is you can go with the H infinity controller based KD controller, which has the inherent capability to reject this disturbance, provided you should be knowing the bounds of the disturbance. If you know the bounds of the disturbance, more specifically upper bound of the disturbance, then you can go for the H infinity controller based PD and PID controller to reject the active disturbance.
Okay. Next question is, which type of control is used for target locking in cruise missile, and in what in case of multiple missile for single target?
Okay. So which type of control you use to target locking in cruise missiles? In general, if you see the literature, whether the missiles by various defense organizations throughout the world, nobody tells which actual control they are using. However, as I told that in most of the cases, as far as my information is concerned, uh, they are still going with the PI control itself. There are two loops in that particular target locking. The one is the trajectory. The outer loop is the mark guidance or the guidance loop for the trajectory loop, and the inner one is the control loop. So in most of the cases, PI control works, but that's what in the literature says. But what I came to know through some of the experts in this defense area, that they are exploring the combination of dynamic inversion along with the mu synthesis controller or the HNFD controller. And what was the second question? Multiple missiles per
And
single car.
yeah,
Yeah,
yeah, and
yeah, you can
what?
extend. Yeah, yes, you can extend the similar concepts what has been explored. But however, here the idea is to here is the multi-agent control technique. That means you can say that one such technique is one can use the synchronization of the multi-agents. So it has been cyclic pursuit is one such field one can explore to have this multiple missile single target. That means so the multiple locations, if one want to converge to the single target with in a synchronous way, then one can use the concept of multi-agent control, and one can use the cyclic pursuit as well. So if you want more, if you want to explore further in this area, you can see the research work of Professor Devashish Ghosh and his team who have closely worked in this area, multiple missiles to single target, but not for this particular missile application, but they have done for the robotics applications, which can be extended to the aerospace applications as well.
Thank you. Next question is, sir, how to use fuzzy logic in tuning the gains? I think the gains for the PID.
Okay. I'm not a big fan of this fuzzy logic control, but I can tell you that fuzzy logic control, what in general, for example, we have worked on for fuzzy logic for PID controller for brushless DC motor. So there is a standard tool available in the MATLAB where one has to give some fuzzy rules to that one. So what kind of so some fuzzy rules, if you give the fuzzy rules based upon Mamdani, or there are various methods available. So it will give you the to PID gain, and those PID gains can accordingly, that whatever the fuzzy controller, whatever you have developed using the rules, whatever, so it will ensure that it will work in all the operating regions. So unlike the single PID controller, which has a which might fail, for it might only work for one particular range of gains, one particular range of speeds, but it may not work for another. But fuzzy logic controller has its own implication. It can There is a possibility that again, it is fuzzy logic tuning is based upon the various operating points. The gains will automatically, it will be tuned. So in if you see in a system point of view, this fuzzy logic controller PID gains is a complex nonlinear function of various operating points with respect to the gains.
And the last set of questions is related to the demo. They have asked from which version of MATLAB is it available, and is the
Okay.
simulation valid for PI and PD models also?
Okay. So this version, I think from 2011 onwards, it is available. As far as I know, from 2011 onwards, this automated tuning is available. Though I'm using 2018, I think 2011 onwards, it is available. And this someone has asked this that PI and PD model. So let me show you. Just let me open this, and I will demonstrate in a minute how to. Let me share my screen. I don't have the. Yeah, I don't have. Yeah, presenter now. Present now. Your entire screen. So is my screen is visible now? No.
No, Bharani, it's not come.
Okay. 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 Okay.
Yes, it's
Is
coming
it
now.
visible now?
Yeah, yes, it's
Okay.
coming. Thank you.
Okay. So somebody asked the PI, PID controller and so on. So the only thing is double click this one. There are several options here. You can see in the top there is PID controller. If you want to select only PI, just select this PI option. If you want, and suppose if you want PD controller, just select this PD controller. What this will ensure that it will automatically, if you are using PI controller, it will automatically ensure that derivative gain is 0, and accordingly it will show. If you select PD controller, it will automatically ensure that the integral gain is 0, and it will give you the corresponding yeah, the corresponding KP and KD value. Even it is only possible for P as well. You can only use the I as well, and these are the 1, 2, 3, 4, 5 different and options are available: PID, PI, PD, P, and I. And if you want to saturate your, you don't want your control in some cases, specifically in the power electronic cases, or in some cases you don't want your control input to be more than certain values, then you can use the PID advanced, where you can limit the output of the PID controller to certain values. Here there is that upper level and lower level. If you want the constrained control, that is also possible here.
Thank you, Dr. Bharani. It was really an informative session, and also thank you for your patience to stay for answering all the questions asked. Um, Thank you for the wonderful session, and hope we can again collaborate in future for some other events or projects. Thank you, sir.
Sure, sure. Thank you, Elizabeth.
Yeah,
Thank you.
thank
Thank you all the participants for your patience. Though I exceeded for 20 minutes, so sorry for it. But otherwise it is fine. Yeah. Okay.
yeah.
Thank you all. Thank
Thank
you.
you. Thank you.
Thank you.
Participants, the feedback link is shared in the chat. Kindly provide your feedback, and tomorrow we will see at the same time, 10:30. Thank you for your patient listening.